Okay, so in lesson 7, we're looking at another typical example of motion in 2 dimensions, and that's to investigate string and pulley problems. String and pulley problems usually have 2 or more masses and a string that runs over 1 or more pulleys. They can range from being very, very straightforward to very, very complex. And in order to solve these problems, we're going to construct free body diagrams for each object being considered, determine the direction of motion, and then write Newton's laws, F equals ma, for each object. So we have a few guiding assumptions for all string and pulley problems in grade 12 physics, and these assumptions will probably also be true if you take first year university physics. And the 2 assumptions that we always make are that pulleys are frictionless. So when a string runs over a pulley, there's no losses due to friction at the axle or anything like that, and that they have 0 mass. And that strings don't stretch, strings don't have any mass, and that they're infinitely strong, so they're not going to break. And these assumptions basically are always in place for the problems that we're going to do, especially in our course, but they're usually in place too, when you go into first year physics. So having said this, let's take a look at it at a very, very straightforward string and pulley problem. Okay, 2 5-kilogram masses are connected as shown in this diagram. We want to determine the tension that's in this string right here and the friction, the acceleration of the system if we have no friction here. Okay. So the first thing that we're going to say is, okay, let's assume some direction for our acceleration. And I think in this case, it's pretty safe to assume that this guy right here is going to fall, and this guy right here is going to move in this direction. And we're going to say, all right, when we do that, that's going to help us to set some directions, positive direction and a negative direction. So let's look at block 1 and block 2 in turn, and we're going to draw some free body diagrams. Here is the block 1, that's sitting on top of the table. The forces that are acting on this guy are gravity in the downwards direction, the normal force, of course, in the upwards direction, and the tension in the string that's pulling this guy along. Okay, the second block is this one that's hanging. And this guy is experiencing the force of gravity downwards and is experiencing a force of tension upwards. And what we're going to do at this point is we're going to write F equals ma for each of these. In this case, the tension is directly equal to ma, the mass of this block, times the acceleration of this block. A couple of notes. The system is going to accelerate at the same acceleration, okay? Which means that this block will accelerate with the same magnitude as this block. And the reason for that is that because there's one string that's connecting the two. So if this one falls by 2 centimeters, this one moves by 2 centimeters. If this one falls at 2 meters per second, this one moves at 2 meters per second. And if this one falls at 2.5 meters per second squared, this one's going to move at 2.5 meters per second squared. Acceleration, when you have one string, is constant between the two. The directions that we will set as our positive direction is going to be the direction that this one accelerates. So because tension happens to be in the direction of the acceleration, the tension's positive in this case. We can make a quick substitution for mass, and we'll set this as being equal to equation number 1. Okay? So the tension is equal to 5 times the acceleration. Here's block 2. This case, of course, we've said that the block is going to accelerate in the downwards direction. So we're going to make down positive. So we have two different coordinate systems. A coordinate system for this block and a coordinate system for this block. So here, the force of gravity minus the tension is the sum of the forces. This is F net that's acting on this block. And this is equal to M2 times A. Making a few quick substitutions, we will see that this right here, 49 minus tension, is equal to 5A. And that's equation number 2. And what we've just created for ourselves, a system is a system of two equations, 1 and 2, and two unknowns, t and acceleration. So when we have two equations and two unknowns, we can solve this by the method of substitution. We're going to substitute this value, t, into this equation here. And we get 49 minus 5a is equal to 5a. Bring this to the other side. And we get the acceleration of the system is 4.9 meters per second squared. Our answer is positive, which means that the system actually does accelerate in the direction that we said it did in the first place. So our guess was correct. This accelerates here to the right, and this accelerates down just as we guessed. If we had been wrong in our assumption and the system accelerated in the opposite way, then we would have received a negative value here, and we just correct our assumption. To solve for the tension, we go back to equation 1 and we simply sub in the value for acceleration that we receive. This is back substitution, and we find that the tension in the string is 24.5 newtons, rounding to two significant figures. We get tension equals 25 newtons. And this, in general, is how we proceed with these types of problems. Let's go to something a little bit more complex. Here is a system of masses and pulleys. Okay, we got M1, M2, and M3. And we're going to solve for the tension in each of the two strings. There's one string here, and there's one string here. Not only do we want to find those two tensions, but we also want to find the acceleration of the system. This whole thing is going to accelerate at the same rate. The rate that this falls will be the rate that this moves, will be the rate that this rises. And we know the masses of each of these. This is 10 kilograms, this guy's 5 kilograms, and this guy's 2 kilograms. So the first thing that we do is we say, okay, let's assume a direction for this. Because this is 10 kilograms and this is 2 kilograms, let's say that this one falls and that this one rises. So we can create our free body diagrams. Here is mass 1. We've got M1G, the force of gravity, pointing downwards, and we've got the first tension pointing upwards. That's the tension in this string, T1. Then we go to our middle block. We've got tension 1 pulling in this direction and tension 2 pulling in this direction, as we can see here. One's to the left, one's to the right. We also have the normal force, and we've got mass 2 times gravity, the gravity that's acting on mass 2. Finally, block 3, we have tension 2 pointing upwards, and the force of gravity acting on this guy pointing downwards. And this is the free body diagram for mass 3. We need to take these things, each of these three free body diagrams, and now we construct Newton's second law equation for each of these three free body diagrams. Remember what we've said. Mass 1 is going to fall. So for mass 1, because its acceleration is down, we set down as the positive direction. So here we go for block 1, block 2, and block 3. Here are our F equals ma equations. We set m1g for block 1 as the positive direction, right? So it's going to fall, so we make this positive, which means that tension 1, which is in the opposite direction, is negative. And that's equal to m1a. We make our little substitutions, and we simplify to receive equation number 1. Here, for block 2, we have tension 1 minus tension 2 is equal to m2a. In this case, again, we've said that this block is going to accelerate to the left. Tension 1 is positive. Tension 2 then, which acts to the right, would be negative. And that's equal to m2a. We substitute our value for mass, and we have equation number 2. For block number 3, we do the exact same thing. In this case, however, block 3 rises, so the positive direction for this block is T2, and the negative direction is downwards, which is gravity. So we write T2 minus M3G is equal to M3A, and we make our little substitutions, and we arrive at equation number 3. What we've just created by doing this is a system of 3 equations, 1, 2, and 3, and 3 unknowns, T1, T2, and acceleration. 3 equations, 3 unknowns, we can solve these. So let's substitute 1 and 3 into our equation number 2. And here's what it looks like. 98 minus 10a, which is T1, minus 2a plus 19.6, which is equation 3, is equal to 5a. Get rid of the brackets, collect like terms, and we arrive at acceleration being equal to 4.6 meters per second squared. Now that we have this, we back substitute into equation 1 and into equation 3, and we get T1 equals 52 newtons and T2 equals 29 newtons. And there it is. So again, this is a little bit more complex, and we still arrived using the same process, just a couple more steps, at a value for acceleration and a value for tension. Okay, example number 3. This is the second last example. But here, what we're going to do is we're going to say, all right, we've got an inclined plane, and we've got a mass that's hanging down. We've also got friction between the plane and M1. This is all the concepts from this lesson, all the concepts from last lesson, and we've rolled it into one. And here we're going to follow the rules for both yesterday's class and the rules for today's class. We're going to follow a blended process. M2 is 15 kilograms, as the question explains. M1 is 2 kilograms, as given. So let's make an assumption then that M1 is going to accelerate up the plane. Even though gravity is pulling it down, it's going to accelerate. We're going to make the assumption that it's going to accelerate up the plane and that M2 is going to fall. Now, if these two masses were closer, it might be more tricky to tell. Okay, but for right now, we're going to stick with an assumption that this is a pretty safe assumption. This one's going to fall. It's much heavier. This one's going to go up the plane. So again, free body diagrams now for M1, which is right here, and for M2, which is right here. So let's go over these. What is pulling M1 in the X direction? Well, I got tension pulling up the plane. I've got friction resisting that slipping and acting opposite to tension. And I've got the X component of gravity, mg sine theta, pointing down the plane. The normal and the Y component of gravity are acting in the Y direction. Here is my free body diagram for mass 2. In this case, I've got mass 2 times gravity. So this is the force of gravity pulling down, and I've got the tension in the string pulling up. What I would like you to do, now that you have the free body diagrams here and here, is investigate for yourself how I construct F equals ma for this and F equals ma for this. So if you can't remember how to do an inclined plane and F equals ma, then go back in your notes and take a look at how we did this last lesson. This one should be pretty straightforward. The answers are 27 newtons and 8.0 meters per second squared. When you've done this, we'll try and look at a full solution in class tomorrow, especially for people that got stuck, and we're going to revisit. This is about as complex as it gets with these types of questions. You can't have too much more going on. So try and prove to yourself that this is the answer that you're going to get.